Section 6.3 is about a type of expression we've seen for those of you who took Math Sec 4 last fall. And it's about logarithms. And logarithms are related to exponential functions. And I'm going to show you how. So maybe just to start, let's remember what an exponential function is. And in particular, I want us to remember what its graph is. So we've got basically two types. F of x is either b to the x, where b is greater than 1, in which case the graph of the exponential function looks like this. Again, always going through 0, 1. Okay. Notice I didn't put any a here in front. It's just b to the x, so it goes through 0, 1. And then the other case is where b is between 1 and 0. And in that case, it's a decreasing function, but again going through 0, 1. But what's interesting to notice is that this function satisfies the horizontal line test. So if I draw a horizontal line, it's going to intersect the graph in only one point all the time. And if you remember, this horizontal line test is a test we perform to decide if a function is one-to-one. So that makes our function f of x equals b to the x, no matter what the case is, a one-to-one function. So an exponential function is a one-to-one function. And the idea is that since it's increasing or decreasing only, it's going to satisfy the horizontal line test. Since it's there's a word for that in mathematics. When it's either just increasing or just decreasing, we say it's monotonic. It satisfies the horizontal line test. Okay, so that means it has an inverse. So therefore, it has an inverse. Okay, great. So let's take a look. And in a specific example, let's say we've got f of x, which is 2 to the x. Okay. For example, if x is 3, f is going to this input 3 is going to have an output of 2 to the 3, which is 8. Okay, and that means that if 8 is the input for my inverse function, it's going to have an output of 3. Okay, graphically, okay, it means that, okay, let's say this is the graph of f, but actually it is, right? It's an exponential function with a base that's 2 here, that's greater than 1. Okay. And maybe let's add the point we just talked about, 3, 8. 3, 8, let's say 3, 8 is here. Okay. To graph the inverse function, okay, of 2 to the x, maybe I should add it actually, y equals 2 to the x, or maybe just y equals f of x equals 2 to the x, like that. To graph its the graph of its inverse function, I need to draw the line y equals x and reflect this graph across the line. In other words, doing that, we are more or less interchanging the coordinates of any point on the curve. So 0, 1 is going to go towards 1, 0. And 3, 8 is going to go to 8, 3. Okay, and then that's going to create a curve that's like this. The other thing that's interesting to notice is that for y equals 2 to the x-axis is a horizontal asymptote. And by reflecting that asymptote across the line of y equals x, we get the y-axis, which is going to be an asymptote for our inverse function. but it's a vertical asymptote. Okay, so this is y equals f inverse of x. Now this inverse function is so famous that it has its own name, its own special notation. Okay, so f inverse is so important that it has its own special notation. So we're not going to write f inverse. Okay, so instead of f inverse of x, okay, so the notation for the inverse function is log for logarithm. So that was the title of this section, logarithm. Now, of course, the inverse is linked to the base of the original exponential function, right? So if f of x is 3 to the x, then the inverse is different. So we're going to put a little 2 here to say, hey, the base of the original exponential function was 2, and we put just x here. Okay, so you should read this as log in base 2 of x. So maybe I should write that down. So this is log, or maybe the exact word is logarithm in base 2. Base 2 because 2 is the base of the exponential function, base 2 of x. Like that. Okay, so I'll show you some examples again. Let's say I want to find f inverse of 8 using, so f is still the, so I wrote example, but let's keep going with that, the previous example. So f is the function 2 to the x, so its inverse brings 8 onto 3. So this is what was shown in the diagram. Okay, so let's write this using our new notation. Okay, so f inverse is log in base 2 of 8 is 3. This is how we should read it. And this one is true, right? Because so this is equivalent to saying that f of 3 is 8, right? So if you go back to the diagram, 3 is sent onto 8, so 8 is sent onto 3 by the inverse. But so saying that the inverse of 8 is 3 is the same as saying that f of 3 is 8. So in other words, if 8, 3 is a point on the curve of the inverse, then 3, 8 is a point on the curve for the original function. Now, going back here, this is equivalent to, let's just translate f of 3 equals 8. This means 2 to the 3 equals 8. So a logarithm, so one thing you should remember, and I often see students forgetting about that or never having seen it, is that a logarithm is an exponent. Notice how this 3 here, so the value of the logarithm is an exponent. It's the exponent to which you raise the base in order to obtain the input. Okay, so we'll look at some other examples of that later, but I'll remind you of that. Okay, a logarithm is an exponent. Okay, so if you can remember one thing right now, it's this. So therefore, in general, okay, if I write y is the log in base 2 of x, okay, you should think, oh, okay, that means that okay, that y is the exponent to which I raise 2 in order to get x. Okay, if I write in general log y is log in base b of x, then y is the exponent to which I raise the base b in order to get x. So we can always translate a logarithmic equation into an exponential equation and vice versa. So you'll have exercises that will ask you to do this. Okay. So maybe maybe let's do one like right now. So convert to an exponential notation. And for those of you who have been with me in the fall, we've done this. Okay, this is actually part of Sec 4. So if I write y is log in base 4 of 15, okay, let's say, then that means y, I'm going to convert it to an exponential equation. So y is the exponent. So remember, the log, which is y, that's an exponent. It's the exponent to which you raise the base 4 in order to get 15. And vice versa. I could convert to an exponential, to a logarithmic equation. So I could say convert to a logarithmic equation, and could be I say 2 to the I don't know, 2 to the x equals p. Okay, could write that 2 to that. So how would I convert this? I would say that x is the exponent, so that x is my log. It's the log in base 2 of p. So it's the power to which it's the exponent to which I raise 2 in order to get p. Okay, let's do some other examples. Let's say I want to calculate log in base 3 of 27. How do I do that? Okay, well, I could. So maybe the exercise here is find, maybe we'll have actually many examples. Log in base 3 of 27. So if you want, you can write y is log in base 3 of 27. Convert this to an exponential equation. That means y is the exponent to which I raise 3 in order to get 27. And then at this point you must realize, oh, 27, oh, actually this is a power of 3. This is 3 to the 3. So we can identify y with 3 now. So the answer here is, so log in base 3 of 27 is actually 3. Let's do another one. Log in base 10 of 0.01. Okay. Maybe write that equal to y and convert this to an exponential equation. So y is the exponent to which I raise 10 in order to get 0.01. At which point you should realize, oh, 0.01, this is 10 to the minus 2. Oh, and then equating the exponents because they have the same base on each side means that y is minus 2. So that means log in base 10 of 0.01 is minus 2. So it shows you a log can actually be a negative number. That's possible. So this is equivalent to just writing log of 0.01 equals 2. So when we omit the base, automatically it's 10. Okay, so if we omit the base, it is 10. Okay, in fact, there is a button on your calculator, log, log, and that's just log in base 10. Let's do another one. Log in base 1/2 of 2. So again, we can make that equal to y. And then we say, okay, y is the exponent to which I raise 1/2 in order to get 2. Now at this point, we should realize, oh, actually, well, I'd like to have the same base on both sides to compare exponents. So I could say, oh, actually, 1/2, you know what? This is 2 to the minus 1. Okay, so in fact, this is 2 to the minus y is 2 to the 1. So that means minus y is 1, so y is minus 1. So that means that log in base 1/2 of 2 is minus 1 because minus 1 is the exponent to which I raise 1/2 in order to get 2. Okay, maybe let's accelerate a little bit and see if we get better at this. What's the log in base 7 of 49? Okay, so I should have written, this is C here, this is D now. Log in base 7 of 49. Okay, so we're trying to find an exponent to which we raise 7 to get 49, which is actually a power of 7. So we can actually see this power is 2, because 7 to the 2 is 49. Okay, so this is actually 7 to the what is 49. That's one way of actually reading log base 7 of 49. What's log in base 6 of root of 6? So 6 to the what is root of 6. 6 to the what is root 6. 6 to the 1/2 is root of 6. Okay, so we can have fractional values for our logarithms. And maybe a very trivial one, log in base 7 of 1. So here it's asking 7 to the what is equal to 1. Can you figure that one out? So I need to express 1 as a power of 7. So this is 7 to the 0. So it's 0. And in fact, it's 7 is nothing special. So we can actually frame this. Log in base b of 1 is always going to be 0. Okay? This is actually, if you think about it, saying that 1, 0 is on the graph of any logarithmic function. So going back up there, you see how 1, 0 is actually on the graph of my inverse, no matter what b is. So here b was 2, but even with b equals to 3, it would still be there. Because 0, 1 is the y-intercept of the exponential function. So 1, 0 is the is part of the curve for our logarithmic function. And that just means log in base b of 1 is 0, right? Or in other words, f inverse of 1 is 0. So no big mystery here, but it's something we should remember. Okay, so in general, if I have and we'll focus mostly on b positive, b not positive, but greater than 1. So here it's increasing. So this is my exponential function. So my logarithm will look like this. So I'd like you to think about a logarithm as a curve that goes like this. So the y-axis is a vertical asymptote. And here there's no horizontal asymptote. It just keeps on increasing, but very, very slowly. Okay. Okay. So that's because this one increases very steeply. So the other one, okay, will increase very slowly. So this is y equals log in base b of x. It goes through 1, 0 because log in base b of 1 is 0. And then we can look at like some of the behaviors. So when x goes to infinity, log in base b of x will go towards infinity as well. Okay. Well, this is actually because if you think about it, for our exponential function, when x goes to infinity, b to the x will actually go towards infinity. Okay, so here we just have to flip those around because of the inversely, we switch the infinity well, this infinity goes here and this one goes there when we actually write it for our inverse function. So maybe here it's less obvious, but let's look at what happens here for our exponential function. So when you go to minus infinity, the exponential function goes towards 0. So now we're going to flip this around. So when x goes towards 0, then see how this goes here now? Then that means our logarithm is going to go towards minus infinity. Okay, so two things to frame here. This and this. So that's important, but it really follows from the graph of the exponential function. And in fact, there's actually a little notation we're going to add. So when we're approaching, when we're getting close to 0 here, we're getting close to 0, but we're positive. So we're going to put a little plus sign here. just to say this is close to 0, but x is actually a positive value. Maybe to finish, number e. So there's a number that's kind of special. So you know how pi is like 3.1415 and like many numbers, and it's actually part of the irrational numbers. Okay. There's another number that's part of the irrational numbers that's quite famous. It's called e. E for Euler's number. Euler was a famous Swiss mathematician. Like when I say famous, I mean really, really famous. One of the top mathematicians of all time. And it's 2.71 something. I have it here, 71828. But the idea is that it's like pi. There's no pattern in the decimals. Okay, I wrote equal, I meant element of. So it's also element of the irrational numbers. In other words, you can't write it as a ratio of two integers. Okay, because if you could, then the decimals would end, or there would be a pattern. Okay, they would repeat themselves. But here they don't. Like those two numbers have decimals that don't repeat themselves. So we're going to see in calculus where e comes from. So right now you just have to believe me that it's an important number. And just like log on a calculator has its own button. So the log is log in base 10, right? So for log of x is log in base 10 of x. There's another button on a calculator. It's called ln. Okay. So ln of x is actually the log in base e of x. And yeah, so just mentioning that there's these two important logarithmic function. So they both look like this because the base for those logarithms are they're both above 1. So they're both the inverse of a function, an exponential function that looks like that. So both graphs have this aspect. So if you want, this is like log in base 10 of x, and ln of x will also look like this. So we're gonna study a little more those graphs in the next section, but this is something you have to know, especially when we're going to want to calculate logs using our calculator. We need to know there are two buttons for logarithms. So that was a long section, but there was a lot of little things to mention, and not a lot of great problems. So we're going to do in the next video a problem that uses logs that's pretty interesting.